Okay, this video is looking at the third reason for electrolysis, producing chemicals that are highly reactive, like sodium. This particular video is looking, there are two different sorts of electrolytes that we can have: aqueous with water present solutions, or the electrolyte has to be a liquid. The ions have to be moving. So if some of them don't have any water present, so to have the ions moving, then the salts are heated until they become a liquid. So they're melted or molten salts. So the states for these would be liquids, whereas this is dissolved salts, dissolved in water, so the states is aqueous. So this video is looking at aqueous, ones where there's water present, and we're making sodium hydroxide and chlorine in the one diaphragm cell. Okay, so sodium hydroxide, normally in the lab it's a sodium hydroxide solution, so sodium ions and hydroxide ions dissolved in water, quite concentrated. It's caustic, so it burns your skin, and if you evaporate the water, then you make like a salt, like any normal salt. So sodium hydroxide crystals. Alright, so this is the diaphragm cell. It's in your textbook on page 247. The fact that it's electrolysis, this power supply has been left off, so I've just added it on. So you can see that the electrons coming from this side of the power supply to here. So this is undergoing reduction, it's the cathode. So on the cathode side, the reaction is producing hydrogen ions, and we're going to end up with hydroxide ions. This is a salt water solution, and you can see on this side too, there's a gas being produced on the anode. So oxidation's happening here, and chlorine is being formed. Okay, so come back to this slide if you need to when doing the written information. So to make sodium hydroxide and chlorine, you use a salt water solution and inert electrodes, platinum or carbon. So the chemicals present are only sodium ions, chloride ions and water. So we need to look at the electrochemical series and work out how the hydroxide is made. So if you find them, you've got chlorine ions here, sodium ions down the bottom here, and water here as well. So we've got water on both sides. So if we have a look at the oxidizing agents, the water is a stronger oxidizing agent than the sodium, so it undergoes reduction first. In preference, it produces hydrogen gas and hydroxide ions. So already we've got one of the things that we wanted, sodium hydroxide produced. The sodium, nothing happens to the sodium ions, they don't react, so they're left there, and hydroxide ions formed in these sleeves. So all seems well, except if we look at the reducing agents. The strongest reducing agent is water. So the water would undergo oxidation and produce hydrogen ions, which is an acid. So the hydrogen ions would diffuse across and react with our hydroxide ions, base that we want, and produce water. So you would be removing the hydroxide ions that you've just formed. So if we analyse this a bit more, the chlorine and water reaction are very, very similar in E0 value. The voltage between them is quite close. So in reality, some of this reaction would be happening instead of this reaction. The more of this reaction that can happen, the more that we get the electrons from the chlorine ions rather than from the water to supply to the water here, the less this reaction would happen. So if this reaction happens, you make chlorine gas, which leave, and you don't make hydrogen ions, which would react with this. So to force this reaction to happen more, If the solution is more concentrated than a 1 molar solution, so 1 molar solution is the difference in E naught values, but if it's more concentrated than 1 molar, then this would be even closer or even swapped, and the chlorine reaction would be happening instead. So to make sodium hydroxide, the solution has to be more concentrated, a lot more concentrated than a 1 molar solution, to prevent this reaction occurring. So if we have a look, our reduction reaction, the cathode here, is making hydroxide ions. The hydrogen gas is leaving, so you're left with hydroxide ions. You had sodium chloride, so now you have sodium hydroxide. On this side of the reaction, the chlorine ions are losing the electrons, being forced to lose the electrons, and the chlorine has now become chlorine gas. So this membrane helps to keep the sodium hydroxide separate. So you have a concentrated saltwater solution to make the sodium hydroxide and chlorine commercially. The chlorine prevents some of the water from making hydrogen ions, which would react with that, and the chlorine turns into a gas and leaves, so it doesn't contaminate it, and what's left behind is sodium hydroxide solution. So can you answer this question? Why is it important that sodium chloride solution be concentrated when producing sodium hydroxide? This membrane I was talking about before is a semi-permeable membrane. Permeable means that things can move through it, it's permeated, but semi means only some things can move through it. So the products of electrolysis can't mix, or they will react spontaneously. So the chlorine gas and the hydrogen gas can't mix in here, they have to be separated, so they can't move through this membrane. The hydroxide ions also can't move through here. So this membrane only allows cations to move, so the sodium, which is a cation, moves across. So there's sodium already in here, sodium chloride, but more sodium would move across, and it would make sodium hydroxide. So you've made the hydroxide from the reaction, and you're adding sodium ions to the hydroxide that's been formed.